Okay, let's dive into this. You know, we all use averages, right? Average temperature, average score, average price. They're super useful for getting a quick snapshot. But what happens when that snapshot is, well, kinda lying to you? Today, we're gonna go beyond the average to find the real story hidden inside the numbers.
So, let me start with a little puzzle for you. Imagine two basketball teams, and they both average exactly 50 points per game. Now, on the surface, you'd probably think they're pretty evenly matched, wouldn't you? But are they really?
Okay, let's pull back the curtain. Check this out. Team A, we'll call them the consistent crew, is exactly what they sound like. I mean, they score right around 50 points every single game. You know exactly what you're going to get. But then you have Team B, the wild cards. Just look at these scores. One night they're on fire with 100 points, the next they completely crash and burn with 0. They have the exact same average, but it is a totally different story. This difference, this spread in the data, that's the hidden story we're hunting for.
To really get a handle on that spread, we're going to need some tools. And we're going to start with the simplest, most intuitive one in our toolkit, the range.
So what is the range? It's honestly the most basic way to see the spread. You just find the absolute highest value, find the absolute lowest value, and calculate the distance between them. It's kind of like measuring the wingspan of your data.
Let's go back to our super consistent Team A. Their highest score was a 52, their lowest was a 48. So the range is just 4, a teeny tiny number, which just confirms what we already suspected. Their performance is really tightly packed and predictable. Seems simple, right? Effective. But that simplicity, well, that's also its biggest weakness.
Just watch what happens here. A new star player joins the team and has one incredible game, scoring 100 points. The rest of the team is still doing their thing, playing consistently, but boom, suddenly our range explodes from 4 all the way to 52. Just one single data point, what we call an outlier, has completely warped our picture of the team's spread.
And this is the crucial takeaway right here. The range is just easily fooled. It's not what statisticians would call resistant. Because it only listens to the two most extreme voices in the room, it can give you a completely distorted picture. We need a smarter tool, one that actually looks at the entire team.
And that brings us to the gold standard for measuring spread, standard deviation. This is the tool the pros use because it doesn't just look at the extremes, it considers every single data point.
Now, don't let the name intimidate you. The concept is actually really intuitive. Just imagine the average is like a central magnet. Standard deviation basically measures, on average, how far each piece of data is from that magnet. A small number means everything's clustered super tightly around the center. A big number means all the points are scattered far and wide. Now, there's a quick but really important distinction we need to make. Are you looking at the data for everybody involved, the whole population, or are you just looking at a smaller group, a sample? Look really closely at the formulas here. For a sample, we divide by n-1. It seems like such a tiny, insignificant change, but it turns out to be incredibly important.
And yeah, that's the question literally everyone asks. It feels a little weird, doesn't it? Why subtract 1? Why would you make it more complicated?
Well, the answer is all about being honest with our data. Think about it. A small sample probably isn't going to capture the full, wild variety of the entire population. It's just less likely to catch those extreme outliers. So by dividing by a slightly smaller number, n-1, we gently nudge the final result up a tiny bit. You can think of it as a mathematical honesty adjustment that gives us a much better guess of the real spread.
Oh, and a quick heads up, you might also hear people talk about something called variance. Don't worry about the details, just know that it's the standard deviation squared. It's a critical step in doing the math, but for actually understanding our data, like our basketball scores, we stick with standard deviation because it's in the same units as our original numbers. It just makes more sense.
Okay, so we've got this awesome, powerful tool. Now what? How do we actually use standard deviation to make useful predictions? Well, it turns out there are two fantastic rules of thumb that really bring this whole concept to life. We've got two main options, the empirical rule and Chebyshev's inequality. And you can think of it like this. The empirical rule is like a specialized scalpel. It's incredibly precise, but it only works on one specific type of patient. Chebyshev's, on the other hand, is like a Swiss Army knife. It works on absolutely anything you throw at it, but its predictions are just a little bit less precise.
And this is the big, non-negotiable catch for our first rule. The empirical rule is amazing, but it has one critical requirement. Your data has to look like that classic bell curve. It's got to be symmetric, with most of the values all clustered right in the middle.
So if you've got that perfect bell shape, the rule tells us that about 68%, More than 2/3 of all your data points are going to be found within just one standard deviation of the average.
Now, if you widen that out to 2 standard deviations, you've suddenly captured about 95% of your data. This is the one you probably hear about the most. It's the foundation for things like confidence intervals and the margin of error you see in polls.
And if you go all the way out to 3 standard deviations, you've pretty much accounted for everything, a staggering 99.7% of all the data. Anything outside of this range is considered extremely rare in a normal distribution.
But what if your data isn't a perfect bell curve? I mean, what if it's lopsided or skewed or just plain weird? No problem. That's where our rugged, all-terrain tool, Chebyshev's inequality, comes to the rescue. Its superpower is that it works for any distribution, no matter what it looks like.
Now here's the trade-off. Where the empirical rule gives us a precise about 95%, Chebyshev's gives us a minimum guarantee. It promises that for any dataset in the universe, at least 75% of the data will fall within 2 standard deviations. It's a more conservative promise, for sure, but it's a promise that is never, ever broken.
So, over the last few minutes, we've built out a fantastic little toolkit for looking beyond the average and really understanding the spread, or dispersion, of our data. Let's do a quick recap of how to choose the right tool for the job.
Okay, so here's your toolkit in a nutshell. Use the range when you need a quick and dirty glance, but always watch out for those outliers. For any serious analysis, standard deviation is your go-to powerhouse. If you're lucky enough to have nicely bell-shaped data, the empirical rule gives you incredible precision, and for literally any other data shape in the world, Chebyshev's gives you a universal guarantee that you can always trust.
So, I'll leave you with this thought. The average salary in a company could be hiding massive inequality between executives and employees. An average 4-star product review could actually be hiding a bunch of 5-star reviews and 1-star reviews. People either love it or hate it. And 2 basketball teams with the exact same average can be worlds apart. Now that you know how to look for the spread, how is this hidden story going to change the way you see the numbers all around you?